Hello, today we're going to talk about types of waves. All right, the first thing we're going to talk about is wave motion. So every wave requires, the creation of a wave requires an energy input from an outside source. All right, so that's basically an initial disturbance. That's what every wave needs to start. So you have a rope, you've all seen this before. You grab the end of it. The initial disturbance is right here with your hand. Flick the rope up, and it creates a wave. All right? If I just do this one time, this is called a pulse. So I have a old soccer goalie jersey. It's a string. All I do is pulse it once. That's a pulse. Now, what you usually see is more pulses put together, and that's called periodic energy from an oscillating source. So basically when you oscillate, so I move my hand up, down, up, down, up, down, up, down, up, down, it creates a wave. Granted, it's a small wave, it's just an example, but it's just a continuous set of pulses is what a wave is. So this is just one pulse, but then if I oscillate it, so all this is, it's all a wave is. A wave is just a bunch of oscillating pulses. Up, down, up, down, up, down. So the motion will be the same at both positions. So at the top and at the bottom, peak or dip, the energy, motion will be the same at both positions. Yeah, I already said that. All right. All right, the first wave we're going to talk about is a transverse wave. So a transverse wave causes particles to oscillate up and down in a direction proportional to the direction of the wave. So, I actually already drew a transverse wave. Let's stop it right there. So what it means is you have this little line that goes through here. At this line, whenever the wave hits it, it's at what is called equilibrium. So it's at equilibrium right there. There when it starts. And right there and there. I'm just going to write equilibrium. So these waves are perpendicular to direction of travel. So direction of travel is going this way. The wave motion is up and down, perpendicular to the direction of the motion. That's what a transverse wave is. It's called a lot of different things. For this, these are called peaks. They're also called crests, whichever one. Down here at the bottom, these are called dips or troughs. And there you go. I think that's all you need to know. So just know this is equilibrium. Whenever it gets to this middle, that's the resting line is what I always call it. Peaks or crests, dips and troughs. Oh, wait, ignore that thumbs up. So, an example of a transverse wave is a secondary wave of an earthquake. So once that initial earthquake hits, which is actually a longitudinal wave, which we'll talk about, after that, the rest of the energy gets distributed out and moves along because it's rock and it can move through that rock pretty easily. So a secondary wave is a transverse wave in an earthquake. All right, the next wave we're going to talk about is a longitudinal wave. So a longitudinal wave causes particles of a medium to oscillate back and forth in the same direction as the wave motion. So this is usually demonstrated with a slinky. I don't have a slinky with me. My children like to break them all. So they're demonstrated. They usually look like this, which looks much different than a transverse wave. All right. So these areas right here, where they're closer together, these are called compressions. These areas where they're more spread out are called, let me build it all up, a rarefaction. Alright, so when you have a slinky, take the slinky and you just, well, you can have it on the table and you send energy from one side. That's your initial disturbance. What you see is that energy go all the way down, hit, and start coming back. Alright, it's a rare, it just sends a compression all the way down, and as that compression hits that spot, it compresses, and then as it goes by, it becomes a rarefaction. So you can just pulse it that way by pushing it in the same direction that it's going. Whereas the transverse wave was perpendicular to the direction, this moves in the same direction. It sends energy in the same direction as the motion. An earthquake is, a primary earthquake is a longitudinal wave. There you go, that's all you need to know about longitudinal waves. Great. Alright, another type of wave is a circular wave. The circular wave causes particles to oscillate both parallel to the direction of the wave and perpendicular to the direction of the wave. A lot of this is seen in the ocean usually. And that's really all you need to know. So basically the energy is going everywhere, it's moving all around. You usually see this in the ocean, but if you actually see it, you take a rope and you kind of, there's that old, I could never do it, but it's a long string, it has a ball at the end of it, and you can send energy down it, or you can flick it in a way that it pulses, it takes in, the ball flips over and makes a knot. I could never do it. My old principal was really good at it. I couldn't do it though, but that's it. So you take a rope and kind of whip it, it creates that circular motion, and that's a circular wave. So wave types and medium. So in a transverse wave can go long distance through rock, can't travel through the core of a liquid or a gas. Longitudinal can travel through all medium, but it's less dense. The less dense that the medium is for it, the less efficiency. And circular waves can travel through all medium, it moves in all directions, it moves all the way around. So all of these, basically what that's saying is, these are all mechanical waves, and all mechanical waves need a medium, like the actual electromagnetic that we'll talk about before. So all these waves need a medium to travel through. Yes, so transverse is good through rock, can't travel real well through the core of a liquid and gas. Longitudinal, the less dense whatever the medium is, the less efficiency it has. And circular can travel through everything. Alright, this has been types of waves. Hope it helps. Good luck.